Oh, now it is.
Oh, no. Okay, there it goes.
Hi, Jackson.
Hey, Jack.
Hey, Jack, just so you know, we're live too.
Oh.
Don't say anything you don't want on YouTube. Hi, Frank. Hi.
So I will be a minute because my sound I just need to sort out. So I can't actually hear anything anyone is saying.
People are starting to pile in. What's the topic of today? Is it a secret?
Is it only me, or does your sound bad to everyone else?
My
as well?
sound?
Yeah, well, maybe it's my computer then. Everybody sounds very choppy to me, but not like in a bad
Sounds
connection
great.
way.
What's the topic?
Doesn't matter then.
I think it might be you. 'Cause everyone sounded okay to me. Well, unless it's me.
Your sound bad?
My sound?
Yeah, well, maybe it's my computer then. Everybody sounds very choppy to me, but
So-
not like in a bad connection way.
So quick check, I also want to check, can you hear me?
Yes,
You sound good right now.
you sound good, Robbie.
Or who are you talking to, I guess, that's the,
I'm
I was talking to Jack, so if you missed that, yeah, Jack's having a little audio trouble. I think he might have a connection issue or something.
okay.
Hi, cat or dog?
So quick check, I also want to check.
Tiny dog. His little tiny dog.
Someone is,
You sound good right
there's a
now.
lot of feedback from someone.
Who are you talking to, I guess, that's the.
I was talking to Jack, so if you missed that, yeah, Jack's having a little audio trouble. I think he might have. I think that's Ravi actually.
Okay. I think I am set. I should just check is.
Yeah, I think you're good.
So just before starting, I also want to say this is not my final mic, but I do now have a mic. So at least a temporary one. So I want to check that this actually, that this works. So it sounds like you can hear me and the sound is
Yeah,
reasonable.
people saying you sound good. So
Okay, that's a beautiful dog, by the way.
Oh, thanks.
It's a
She wants to learn algebraic geometry today, I guess.
Yeah. Always a good dog. That's okay. So
I'm gonna head
should we
over to
do?
YouTube.
Great.
Well, there's no questions. So, and I think it's 11:05. So,
Good.
and there's
We'll just go for it. Okay, great. So,
yeah.
Okay, great. Let's see. Then 1 second. Great. Okay. So, welcome back. This is the 10th of the pseudo lectures, and I wanted to at least suggest a plan for the future as to how this might end, and hopefully it won't end in tears. My idea is that I think it would make sense to have another 3 or 4 more pseudo lectures, because that would roughly bring us to a natural stopping point, which will be roughly this part of the notes, and ideally ending with some actual examples and results that'll tell you things about things you might have wanted to know before. And this won't be the most direct way to show these particular things, but hopefully this entire perspective will make clear that this kind of unifies. It's some sort of grand unification of all these classical, of all these important classical facts. So my intent is to do another 3 or 4 lectures in this series, so definitely will end in September, and the 3 or 4 will depend a little bit on the content. And then maybe after that, then we could start a new edition with whoever wants to, with new people, maybe after a brief pause, starting with a review, but roughly where we're ending on. Okay, so my plan for today is to think basically about morphisms in some detail. And so we know what schemes are, we vaguely know what varieties are, maybe not exactly, and now we will understand the category of such things. Okay, so let me start with with the notion of morphisms of schemes and varieties and try to figure out what our plan should be. And we talked about this a bit last week. So I'll remind you of what we talked about, that the motivation is that, let me maybe, hold on 1 second while I make a better choice of color. Great. So we want to map schemes, and varieties are these ringed spaces. So it's the data of a set with a topology, which we could combine in topological space.
Robbie,
then
are
we
you writing
have-
something?
I am, and that's not good that you cannot see that. Let me, I suspect I know what the issue is. I'm glad you caught that. Let's see. How about now? Not yet?
Not yet, no.
Okay, let's see if I can. I think what I will do.
Yeah.
is-
Did someone
Okay.
already tell you?
Yes. Let me just, let's see. I'm just going to stop and restart my share, and that, at least in the past, has.
Your mouse is on it, by the way. I don't know if that helps.
That is.
I can see your
weird.
cursor right now. Is that it called?
How about
cursor?
now? Still cursor?
Nothing changed. I can still see your.
Okay, stop
mouse
share.
pointer. There.
And then comes the new share.
Now I see stuff.
Yes,
There
now I
we go.
see
I
stuff.
see some sheaves. Oh, let me
Still
mute
cursor?
this. Okay. So
Okay.
it looks good to me. Oh, let's see. Let's see if you can write. And there you go. It's moving back and forth. Great.
Good. Great. Great. Okay, good. So let me just go backwards briefly, just to say what you've already heard me say, which is tentative plan for the future. So this series will end sometime in September. And today we'll talk about morphisms. And right now where we are where we left off is motivating them, where schemes and varieties are ringed spaces. So we'll describe these in terms of ring spaces. So that's our motivation. And the second thing is that we already know that when we have a ring map from B to A, then we get a map of ringed spaces, spec A to spec B. So we've discussed that, and I'll remind you about that. And so we'll want maps of ringed spaces which look like that locally. And then it will end up being useful to actually deal with maps of locally ringed spaces. So it'll add maybe a little bit of confusion, but maybe it'll be less confusion, since one thing I noticed with this series is that you, the audience, forced us into locally ringed spaces earlier than I was expecting, which is, I guess, a good thing. Okay, I hope that is still visible. I just refreshed. So great. So a reminder, because I said it briefly last week about what morphisms of ring spaces are. We have a topological space with a sheaf of rings, and we're mapping another one such thing. And so since we think of ring spaces in terms of sets with topologies, well, we want a map of sets, obviously, and we want it to be continuous. So the set and topology part's taken care of there. And then the additional data we need is that of pullback map, where we have to know how to pull back functions, which means that on any open set, we have functions downstairs. We need the additional ingredient of what the function pulls back to upstairs. And if you prefer, although here doesn't seem to be necessarily immediately useful, although it's always good when you have adjoints to immediately think about things simultaneously in two different ways. One definition I should say is the notion of a ring space over a field. So all that means is a ring space is a sheaf of rings, A ring space over a field would mean a sheaf of rings where all the rings are K algebras. So if you're dealing with complex analytic spaces, you expect to have a ring space over the complex numbers. Okay, so some features of morphisms of ring spaces that we may have discussed before basically is that, first of all, certainly we'd be very upset if you couldn't compose them. So you can compose them and you can think what that means. So you have continuous map followed by continuous map, and the functions pull back, and these functions pull back, so they compose. Another important thing is that the morphisms to a ring space from another ring space glue. So let me say that more precisely, because I think we've discussed this enough that you've seen this before, but it can be very confusing the first time you see it. What I mean to say is that if you have a target space Y and you have a source space, then if you have a map, let's call it X, and let's say you have a cover of X, and then you have maps from each of these things in the cover into Y that agree on the pairwise overlaps, then they agree. So in a fancy way, I could say that they form a sheaf. Maps to Y form a sheaf on X. So, so that's something you always want with any kind of geometric space. Also, one thing we haven't discussed is you can actually, if you have a module on your source ring space, and again, we're going to have our map from X to Y, then the push forward of that module is on the target ring space. And because over any open set on the target, the sections of the push forward F are sections of F upstairs, it's a module over that ring, but that itself is thanks to our definition, is a module over this ring. So in other words, the O module on the source, when you push it forward, becomes an O module on the target. You can push forward not just sheaves or sheaves of abelian groups, but even O modules now. Okay, and then anytime you have a morphism of rings from B to A, then you're going to get a morphism of ring spaces. And here again is Y. So we need to figure out what this map is. And we've already, I need to say what it is on points, then on topologies. So I need to tell you continuous map, but we've done that already. So what's left to do? It's how do we pull back functions? And all I need to do is tell you how to pull back functions on a base of the topology, because that'll tell us how to pull back functions on any union of those open sets. And so I'll tell you, but we already know that from the map of topological spaces that when we pull back the locus of where G doesn't vanish, we get the locus where the preimage of G doesn't vanish. And so what's the map? The map we'll define is going to be sending just BG, which is indeed the section of that open set, and we'll map it to A, the localization of A at the image of G. And so that's what the map's going to be. And that's induced by the map from B to A. So we know all about that. Great. So that gives us a map of ring spaces. And now a reasonable question that I think everyone should ask or will ask at some point, which is that not every map of ring spaces of specs is of this form. And a related question is, well, I need to say this in the right order, but however, once we know what maps of locally ring spaces are, it does turn out that every map of locally ring spaces is of this form. And so, of course, I need to tell you what that is. But even before that, there's a question of, someone will ask then, what's an example of something which is a map of a ring space that's not a map of locally ring spaces, or a map of spec A to spec B that is a map of ring spaces, but doesn't come from the sort of thing we're talking about now, and that's going to be that's a problem on the homework. So it's like a basic example and hard to think of for me because it's by definition not natural. It's a weird thing. Okay, great. So what's a morphism of locally ring spaces? Well, so a locally ring space is a ring space where the stalks are local rings. So it's a morphism of ring spaces such that, well, there's additional condition, which is if you map a point in X to a point in Y, then of course that induces a map on stalks, as you at this point know well. And I'm going to want the maximal ideal downstairs to go to the maximal ideal upstairs. So the translation is I want functions vanishing at Q downstairs to pull back to functions vanishing at P upstairs. And put that way, it's very reasonable. And so I prefer to think about it geometrically like that. Okay, so here's a result which will be maybe one of the more complicated things we'll prove today, which is that if you have a map from spec A to spec B as locally ring spaces, so I'm not saying a priori that it came from this ring map B to A, but if you have a map just as locally ring spaces, then in fact it is the map of locally ring spaces induced by the map of rings. Well, what map of rings? Well, if you have the global section, when you pull back global sections on this, you get a global section on this. So you have a map from B to A. And there it is. So the claim is that just from that single map on global sections, you can recover the entire morphism of locally ring spaces. And that will mean, if you think about it, that the map as every map from spec A to spec B as locally ring spaces corresponds exactly to a map of rings from B to A. Okay, so that's what we want to prove. And there it is again at the top of the page. So suppose we have a map of locally ring spaces, and the goal is to recover this map of locally ring spaces only from the map on global sections. So how do I do that? Well, I need to, so what I need to do is tell you what it is on, tell you the map. I want to recover the map on sets, and then I want to recover the map on topology, I want to recover the fact that it's continuous. I guess that's going to be for free maybe. And then I want to recover the map on sheaves. So if I give you the map on global sections, how do I recover the correct map on sets? Well, what I do is as follows. So if you have P going to pi of P in our map of ring spaces, well, what I want you to do is consider so how do you recognize P? I think of it as I can recognize it by just keeping track of those functions on the space vanishing at P. That's not legible. I don't care. You know what I mean. Vanishing at P. And all I'm doing is I'm reverse engineering, connecting the point to the maximal, to the corresponding prime ideal. So, again, just to be really explicit, this is only because this is a map of, because this is a ring space, the points correspond precisely to the functions on it that vanish at that point. That's the point of the maximal ideal. And so how do I figure out what pi, and ditto, that's how I recognize this. So how do I recognize that P goes to pi of P? At this point, I recognize by all the functions vanishing at pi of P. Let me call it Q. And so how do I, so P goes to pi of P if all the functions vanishing here pull back to functions vanishing here. So I said that terribly. So let me maybe try to say that one more time and see if it all helps. So given a map of locally ring spaces, and I have a P in the source mapping to pi of P in the target, I can discover what those points are supposed to do by looking just at the global sections and noting that those functions vanishing at the target point pull back to the functions vanishing at the source point. Okay, so that is the map of sets. And then the map, I want to mix in the topology and recognize the topology is that coming from the map of rings. And so if I take a basic open set of where the function G doesn't vanish, and this makes complete sense on a locally ring space. So I'm allowed to, so G is a function and I can check where it doesn't vanish. And secretly, I know that's what it's supposed to be on spec A. Well, because of how locally ring spaces work, that's exactly where the pullback function doesn't vanish. Morphisms of locally ring spaces are cooked up to be exactly that the locus for something vanishes, pulls back to the locus where the pullback vanishes, and the locus where something doesn't vanish pulls back to the locus where the pullback doesn't vanish. So topologically, we get the correct notion that we're expecting to see from maps of rings. And the last thing we need to check is that the pullback map on functions on this map of locally ring spaces agrees with what we want it to be if it had come from the map on rings. And so let me just write down what that means. So what we'll do is we will check the sections over. So one thing we know about is the sections over the entire spaces. We have our map B to A from which we're supposed to recover everything else about this map of locally ring spaces. But we already know that if we have an element of B, then so we already know that we should try to recover. Let me write this down, and then okay. So we're trying to recover the map on these basic open sets, and but we already know on these basic open sets that's a G, B sub G, and this is A sub pi sharp of G. So the right side, the A part, that's spec A. It's an affine scheme, and so we already know that the basic open set here has as sections this, and ditto on the left side on the source, we have this distinguished open set, which is on the target because the arrows are reversed, and so we want to check that the pullback map from here to here is forced by this map from here to here, and it is because this is local. Both of these are localization maps. This is localized at G, and this is invert G, and this is localized at G, the image of G. So in other words, if you have a map of modules and that induces a map of localizations, and that tells you what this map is. Okay, so let me sum up because I think that sounded more confusing than it needed to be, and if you digest it, it's less confusing than you think. Maybe the motivation I will say for this is that sometime earlier, I hope you tried the problem that says that the maps from the isomorphisms from A to A prime corresponded exactly to isomorphisms, and I'm going to deliberately write the arrows in the opposite direction, but isomorphisms are supposed to go both ways, specs in the opposite direction. If you did this exercise, which I called a strangely confusing exercise, and I hope you did, then you've seen all the complications that arise here. This is the special case of isomorphisms, and now we're doing the more general case of morphisms because we have language for it, but the argument is the same. And to say it again, you can match up the points purely from ring theoretic information of seeing where functions vanish. And then the topology will be the same because you're dealing with locally ring spaces. And so the basic open sets are going to be precisely where certain functions don't vanish. And finally, for sheaves, on the basic open sets, the distinguished open sets, it's just localization, and that forces what the map on open sets, on smaller open sets looks like. Okay, that's something you have to digest, and so that's the that's substantively the most complicated thing for the day. But once we have it, now we're basically set. We just define a morphism of schemes to be a morphism of locally ring spaces, and schemes are locally ring spaces, so that's completely fine. And we have no mentions of specs, but for free, with this definition, we know that if you have a map of schemes from X to Y, and you're mapping spec A, and it happens to land inside spec B, then for free, because spec A to spec B is a map of locally ring spaces, for free, it looks like the way we want it to. It's going to come from a ring map from B to A, and we have this recipe to turn B to A into a map of, we turn B to A into a map of affines the other direction. So that is good news. And maybe I should also say, if you're thinking about varieties, whoops, that's not what I wanted to do. Then maps of varieties also work as maps of locally ring spaces. So everything I'm saying works just fine if you prefer to be in the finite type case. Okay. Great. So, okay, so what this means is that, just to repeat, maps of affine schemes correspond to ring maps in the opposite direction. I could say this in a fancy way, that the category of affine schemes is exactly the category of rings with the arrows reversed, the opposite category. But a really, really important and really not hard fact when you actually do it is that's true even if you replace spec A by an arbitrary scheme. So in other words, the maps from X to an affine scheme are exactly correspond to maps of global sections in the opposite direction, from B to the global sections. So this is something which you really should do. And just to give you a hint as to how to do it, well, X is covered by a bunch of affines, and these guys can be spec AIs, and then you can somehow try to figure out what's going on here and use the fact that maps of local ring space is glue. So that's basically it. Okay, now here's an advantage of this. One of the advantages in terms of point of view is that we had this old definition. We had this old definition of a scheme. Well, it can't be that old since we're only a few weeks into this, which was it's a scheme where everything involves A algebras. And so now the new version is that an A scheme is just X with the data of a map to spec A, because that's exactly what this is. I guess the B should be an A to make this actually line up. So an A scheme is a map to spec A. So for example, a complex scheme with the complex numbers is nothing more than a scheme with a map to spec of the complex numbers. And then a map of things over the complex numbers are just going to be diagrams that make this commute. And so you can even generalize this and that works for any ring. And then you can even do something like talk about schemes over not just spec A, but replace it by an arbitrary scheme. So the category of S schemes, where S is any scheme, I'm only saying this because it's a useful notion, but there's no additional content that you have to worry about here. So if you're working over something which you often call a base scheme, like spec of the complex numbers, then you have this category of such things. Yeah, there's really nothing there. And now something I don't want to talk about, but I guess maybe I should talk about it a little bit. So there's this notion, in fact, this came up in question period, one of the earlier times, which is what's the functor of points? And I will tell you what the functor of points is now, but I want to say that I understand why it has this name, but now I feel it's not a great name to have. And I would really prefer to call it something, I think of it actually as a functor of maps, and I'll explain why. And one of the reasons this sucks is because there are too many different kinds of points, and that people talk about with schemes. So there are the actual points in our definition. It's a set, underlying set of a scheme. Those are the points. I guess they're generic points, and I'm not so bothered by that because that's just a special kind of. These are examples of the points we're talking about. But if you're dealing with varieties, then when you say point, you mean what I might mean by close point. So that's a different kind of point. And then you also have S-valued points, which is what I'm going to describe here, or even geometric points. And these all mean different things, or related to different things. So it's very confusing. I really prefer just to talk about points as points, and then varieties just being cautious that I'm talking about close points. Okay, so what's a k-value point? If you look underneath my crossed out bit, it's nothing more than a map from spec k to x. And an a-valued point is a map from spec a to x. Then a s-valued point is going to be a map from s to x. And the only variant is a geometric point. When someone says geometric point, what they mean is it's a map from a field, but not just any old field. It should be algebraically closed, or I guess separately closed as well. And I'll leave out why those fields are nicer for perhaps later. But what's the reason for this language? It's the fact that if X is affine, as an example, let me just take X to be the following scheme, spec of, let me do spec of X comma Y mod X squared plus Y squared minus 1. So what's a map from spec of Q to that? Well, as a ring map, it's going to be mapped in the opposite direction, where X will be sent to some rational number and Y will be sent to some rational number, and they'll satisfy this relation. So in other words, it's the rational solutions of this of the equation X squared plus Y squared equals 1. So it's like, so you're finding the rational solutions of this thing, and if you wanted instead the complex solutions, you would replace it by C, or if you want the real solutions, you'd replace it by R. And if you wanted the integral solutions, you replace it by z. So that's, I guess, the reason for functor of points. But really, I think in order to avoid confusion, it's really the functor of maps from spec k into it. And oh, and why is it a functor? I'm not even going to say why it's a functor. It's not relevant now, but if you're curious, I can tell you later. Okay, great. So now, just as a bit of an aside, but kind of an important aside, since lots of people who are watching are complex geometers. So we've already talked about defining a complex algebraic variety. It's a ring space, or it's a locally ring space that locally looks like an open subset of c to the n. Great. So now that's our definition. And so these, sorry, that's a complex analytic variety. And you have a complex algebraic variety, which we've not exactly defined, but if you want, there are things that locally look, well, up to the Hausdorff condition, there are things that locally look like things in complex n space cut up by some equations. So there you can analytify, you can take the algebraic thing and have a corresponding complex analytic space. So, and in fact, this works for any variety. And in the case of an affine variety, you know what you want it to be, which is that if you have an affine complex variety, so it's spec of C adjoins some variables, mod some relations, then really you're thinking that this is inside the analytic version. It's going to be inside in C to the n, and it's going to be cut out by just these equations equal to 0. So you know what it wants to be. But the question is, can you define it for a variety in general? And you might say, okay, cut it into affines and check that everything behaves well. But way better is to do the following thing. And this is an argument for thinking in this way. Okay, so given a complex analytic space, you actually get a map of locally ringed spaces to your scheme. And this is a place where you really need schemes and not you need the generic points as well. Okay, so the statement is that I want to define the complex analytic variety to be something really the data not just of it's going to be a complex analytic variety along with a morphism of locally ringed spaces to X, such that for any other map of a complex analytic variety that maps X, it must factor through this analytification. So that by universal property, if it exists, it's unique of the unique isomorphism. And okay, so why make that definition? Well, it's for the uniqueness reason. But with this definition, it may not be obvious that it captures what you want. Well, then all you have to do is show that the affine, the building block situation, is correct. That this thing that I'm describing is going to satisfy that universal property. And then basically for free, once you unwind the definition, it means that for an arbitrary variety, what you're going to get is something which is glued together from these affines, and all the gluing issues go away. So if you're a complex geometer, this is worth looking at. And I should say Sarah's Gaga paper relating complex analytic and complex algebraic geometry is one of the finest gems of mathematical history in terms of writing, I think. Okay, so that is, so let me, if you're afraid of the complex numbers, let me go back and work, and we'll get nice and classical and talk about projective schemes. So, okay, so now we know what morphisms are, and so projective variety, projective schemes are ways, are machines for building complicated things built out a lot of affines and just capturing it with just a single graded ring. So that's so similarly, morphisms of such things are going to be, I want to understand in terms of graded rings. So I'll tell you how it works basically by just doing two examples, which is imagine you wanted a map from P2 to P1, and I'll tell you kind of what the map is. That's a point in P2, X, Y, Z, and I'll send it to P1, and I'll send it to say X squared minus Y squared, X squared minus Z squared. And this is well defined as if like X is 3, 4, 5, I'll get the same thing as if I put in 6, 8, 10, because these are homogeneous of the same degree. If you double X, Y, and Z, you multiply these by 4. Okay, so that's the thing I want to think of as my map. And is it a map? Well, for most values of X, Y, and Z, it works. But the only way it could screw up is if these are both 0. So what we really need to do to make this work is to throw out the points where both of those are 0. So 1, 1, 1, 1, 1, minus 1, let me just write it this way, 1 plus or minus 1 plus or minus 1. These, if you plug in those points into P2, you'll get 0, 0 here, and that's bad news. But if you don't plug in those points, you don't get 0, 0, and it's good news, and hence you get a map. So somehow the corresponding ring map, and we know what that's going to be, it's going to be, the ring map is going to be in the other direction, and it's going to send u and v to x squared minus y squared and x squared minus z squared. Maybe one thing I should point out that notice that this is degree 1 and this is degree 2, and that's completely okay. That's not alarming. All that mattered is that we scaled by 2. Everything got scaled by 2. They don't have to keep the degree the same. But okay, so given this ring map, what we should recover is there should be a map from P2 to P1 that's mostly defined, and it's defined away from precisely this locus. Okay, second example is the map from P1 to P2. And let's take a map that sends UV to this. And once again, this is going to be well defined because if I triple U and V, I just multiply each of these things by 9. And so I get a well-defined point in P2. And then you may think, uh-oh, what if I get 0, 0, 0? But the only way I can get 0, 0, 0 is if U and V are 0. And then that's not a point of P1. So in fact, the problem in the previous case does not arise. But the reason I give this example is I'm going to point out that the image satisfies this relation, that this squared is that times 4. And what that means is we should get a map not just of graded rings like this, but even from this quotient. And the picture is going to be that this is a P1. When I take, that's what I get out of K join UV. And then what I get out of this is going to be inside P2, but it's cut out by this equation. So it's going to send P1 and end up being a conic in the plane. So that's so these are just 2 examples. And, but with those examples, I want to abstract abstract what works in general, and I'll leave this for homework, but it's not bad homework at all. So if you have any map of graded rings, and I guess these are non-negative graded rings, so we can have them be, and I'll even want them to be finely generated perhaps, but for what I'm saying, this doesn't matter too much. But I want this a map of graded ring is going to mean that you are allowed to scale by a degree d, and it need not be 1, but it should be positive. So the statement is that any such thing is going to induce a map mostly from the projes, except you're going to need to throw things out. What will you need to throw out? You'll need to throw out the things that go to 0, 0, 0, 0, 0, roughly speaking. So that's basically you take the things of you take the things in a positive degree in S, and you want to check, be sure, well, do the homework and just parse this and realize it's exactly the same thing as you saw in the previous example. And in particular, if you get if the thing that the recipe tells you to throw out is empty, then you get an honest map of graded rings, projes, I'm sorry. Great. So now comes another example that came up in questions some time ago, which is the Virenese embedding, or we don't know what the word embedding means. I guess we don't know what anything Varnase means either, but I'll at least say what the map is. So if you take the polynomial map on n+1 generators, and I want to take basically the, I want to choose another polynomial ring, and I want generators for every degree d monomial in these n+1 variables. So there's a lot of them, and it's some nice, beautiful binomial coefficient. That's how many there are. And if you work out carefully what that binomial coefficient is, it's n, or I'll call it n, O+1. And that means that you have this ring map, and this ring map is graded because you send like y sub this thing goes to the corresponding monomial. So it's a nice graded ring map. So we get a map from one projective space to another, and you don't have to throw anything out. And I'll let you think about why that's true. But you're basically just sending x naught to xn to write down all the monomials in order in this monstrously huge projective space. So you're taking projective space and you're sitting in a huge one in some interesting twisted way. And this ends up being a useful tool. It's just projective space in an abstract sense, but it's a useful tool, and that's called the Virenese embedding, and that'll come up later. And just some examples. If you take P1 and you take the degree 2 embedding, what you're going to get is a conic in a plane, and you even know what the conic is, it's going to be xz minus y squared equals 0. Or if you map it to P3, you get what's called the twisted cubic. And if I were to draw a picture, there's P3, and there's your twisted cubic in it. And we've even seen equations for it. And it's codimension 2, whatever that means, and it needs 3 equations. And the degree 2 embedding, Virenese embedding of the projective plane lands in P5 similarly. Okay. So that is what I wanted to tell you about the general theory of morphisms. But there's a variant I want to mention, which are called rational maps. So rational maps, these are not awkwardly, these are not necessarily morphisms. So the informal way of saying maps are morphisms and morphisms are maps are dangerous. So whenever someone says map, then in scheme land, you have to be a little bit nervous that about what they're talking about, because they may mean an honest morphism or they may mean one of these. Okay, but I want to talk about rational maps, and for convenience, I'll talk about reduced and irreducible schemes. So they have one piece that's irreducible, and they have no fuzz, that's the reduced part. And the part that really matters is the no fuzz. Okay, so what's a rational map? A rational map is basically a mostly defined map. It's defined almost everywhere in some sense, but it's allowed to be undefined at some places. And actually, we're not going to really need integral. What's going to matter later is the reduced, although you may even wonder where that comes up to. So what's a mostly defined map? My definition is going to be something which is going to remind you of how we described stocks. So we have, it should be defined on a big open set. So we have a dense open set. I guess I should say dense and open, and a map from that dense open set to Y. But maybe it doesn't extend any further. But I do want an equivalence relation that if you have a dense open set sitting inside 2 other dense open sets, and these 2 maps restrict to the same smaller thing, I guess I should really draw a picture here. So there's X, and there's U, and there's V, and there's W, and then to check whether the map from U to Y is the same as the map from V to Y, the answer is if and only if there's like some smaller open set here that also, that they restrict to the same map to Y. And you may worry that, well, wait, what if I restrict to another different small thing in there that has nothing to do with it? And maybe the maps are the same here and they are different here. And the answer is irreducibility is a really strong statement. There's only one piece, and that means there's any 2 non-empty open sets intersect. So you can't have this picture. Okay, so this should remind you a little bit about stocks. And you might remember when we had a stock, we had a similar looking condition. And so this was a colimit. If you like colimits, it's the fraction field of a ring if you like rings. And so there are a bunch of things which are the same. And so what I'll say now will include things that are, I guess, might be definitions, or they may be obvious depending on your point of view. So if you take the stock, if you have an integral scheme, and you take the stock at the generic point of X, well, what is that? Well, that's going to be a field, and that's we'll call the function field of X, and we'll call it the field of rational functions. And we can compute it by taking any affine open, well, non-empty to be pedantic, and take its field of fractions. So that will be the same as the rational functions in the stock of the generic point. And also, this is the same as rational maps to the affine line. So I guess you could say functions, this is even I guess I even could have said this earlier today, functions correspond to morphisms to A1. Rational maps correspond to rational functions correspond to rational maps to A1. And this is not a statement of something obvious, it's something you have to actually prove, and then it becomes obvious. Okay, let me introduce some more words. So instead of surjective, we have the notion of dominant, and I don't want to say surjective because our maps are only defined up to taking open sets, and so but dominant means the image of anything, any U to Y, where U is inside X. is dense. So that's our definition of dominant. And then you might ask whether it's well defined, and you can think about it, and it is using irreducibility here. And the picture is that it's mostly surjective, except maybe if you have something which doesn't look like it's really geometric, like the spec of the function field, then you have things that are dominant that don't seem to be mostly surjective. Excellent, great. So, and one thing you'll notice is that if you have a dominant map of integral schemes, so in other words, if you have a dominant map from X to Y, and you have any rational map to Y to Z, then you can compose it. If you didn't have it to be dominant, then you might worry that you could have a map from U to Y, and then you have a map from V to Z, and you wanted to compose it, but you might miss V completely. But if you know that U meets every non-empty open set, which is to meet that it's dominant, then we can compose this and take the preimage of V inside U, and that gives us a map to Z. So we can, in that case, define the composition of rational maps. And again, the condition is that the first one has to be dominant, and it can't hurt if the second one is dominant as well, which means in particular we have a category of integral schemes and dominant rational maps, because we know what integral schemes are, we know what dominant rational maps are, and we can compose. Okay, but then as soon as we have a category, we have the notion of isomorphisms in the category, and so that we call a birational map. So a birational map is, again, by definition, it's going to be something which is going to be a rational map from X to Y, such that there is an inverse rational map, which means that the composition rational map is a map from X to X, and it should be the identity, and with the mild caution that X to Y might not be defined everywhere, and yet the composition still counts as the identity, because of all it means is that on a big open set of X, it's the identity. Okay, and then the other definition is that something is rational if it's birational to n space. I should also say birational morphism is a birational map that happens to be an honest morphism. But its inverse birational map might only be a map. Okay, so now this is just a series of definitions, and I'll motivate them a little bit in a bit. So we'll say two schemes are birational if we can find a birational map back and forth between them. And you can check, but just don't read the notes, because that has not the right proof, and I still have not rewritten it, that two integral schemes are birational, which again you should think of as being mostly isomorphic. That if you have two integral schemes are birational, I need there to be a finite, there's a finite, there's a finite type condition. Which we now know what that means as of last week. That two things that are variety-like, basically two varieties are birational if they have big open sets that are actually isomorphic. So it really does mean when you're in a geometric situation that things are birational if they're mostly isomorphic. So for example, something is rational only if it's mostly affine n space. So over like the rational numbers, it means you can find lots of rational solutions. So let me do some examples to try to translate things you might have cared about before into this language. Okay, so cheaply, the plane and P2 are birational. You have birational open sets because A2 even is an open subset of P2, so that's good. Maybe less cheaply and extremely fundamentally that that x squared plus y squared equals z squared in 3 space, and I'll do it over the rational numbers, is rational. And the fact that it's rational is really why we can find a formula for all Pythagorean triples. So this, put differently and in a more correct classical way, is in the notes as well. And as an example, so that that's sort of classical and well known, but thinking about it the right way lets you see that in fact, if you have actually any conic that has a point that has one solution will have infinitely many. That's what will come out of this in the homework. But maybe a variant is that if you had to solve this Diophantine equation, you can solve it and find all solutions, and that'll translate, in effect, the fact that this is also rational. And that means we can solve it over any field at all. However, if you take x to the n plus y to the n equals z to the n, where n is bigger than 2, this thing is not rational. And it's not, it should not be obvious. It's hard to show something is not rational, but in the homework, there'll be a hands-on way of actually doing it. And you'll notice that in the course of doing it, you'll get things that are reminiscent of both Fermat's last theorem, which is easier in somehow geometric variations, and also elliptic curves too. And then one last question is that A2 and A5 are, oh, I know what I wanted to say here. I wonder if the HY is cut and pasted somewhere else. So A2 and A5, one is 2-dimensional space, one is 5-dimensional space. They better not be mostly isomorphic. So my question is, why is that true? It must be true, but can you actually prove that? Okay. And then a useful fact in geometry is that if you have 2 integral finite type schemes, then function field extension. Oh, I think I'm now thinking I didn't need finite type in the previous statement that I wrote, lately added in. If you have an extension of function fields, that exactly corresponds to rational maps in the opposite direction. So inclusion of function fields corresponds to dominant rational maps. I should have said dominant. Dominant rational maps the other direction. So in other words, field theory tells you about mostly defined, roughly speaking, maps of all varieties. Okay, so now let me just set ourselves up for next week. I'm going to describe. So next week I want to describe a lot of useful types of morphisms that are things. Every class I should describe should either be something which you realize is something you might want an adjective for a special class morphism, or it'll be something which should be like a Noetherian ring where all reasonable things should have the property, but you might need that hypothesis. And as an example of one which, so I don't have to define something new this week, are open embeddings, where you have basically an open embedding of ring spaces. And this is like an important class of morphisms. And I want to look at this and also have notice some nice properties that you should expect that will set us up for next week. The first thing I want to say is that before getting there is that there's this absolutely fundamental insight of Grothendieck, which, as with many of his insights, maybe has no logical content, but it's a change of point of view, which is that the fundamental things when you think about something in mathematics, such as, for example, varieties, are not the varieties themselves, but the maps between them, and that's what you should be focused on. So things that you think of as being properties of a variety or a scheme, or take any part of mathematics you're in, really should be functions of maps of them. So as an example, we will see that Hausdorff really should be an adjective for morphism, not of a topological space. Okay, so let me give you examples of things of properties you expect any nice class of maps should have. So you expect so any reasonable map class of maps should be something where if you compose them, let me start with number 2. If you have one open embedding, another open embedding, it's true that the composition is an open embedding. And similarly, if the map of locally ring spaces, you kind of expect there should be like a category of such things. They should be closed under composition. I guess I could also put in the identity should be, yeah, I guess there should be a category of such things. The identity should be an example of any reasonable, the identity should satisfy all, should be an example of any reasonable sort of thing. A less obvious thing is that the notion should be local on the target. In other words, if you have a map from X to Y, and you're wondering whether it's an open embedding, for example, you can check on an open cover on Y, and if it's an open embedding into U and an open embedding into V and so forth, and they cover Y, then it's an open embedding. So you can check everything locally. So that's that. So almost any reasonable thing you can think of should satisfy this too. And actually, if you want another example, yeah, I guess isomorphism is another example. Certainly, you can check if something is an isomorphism. You can check it locally on the target. And isomorphisms are, if you compose two isomorphisms, you get an isomorphism. And then the third thing, which we don't exactly have the language for yet, and so maybe I can't convince you of it, is that it should be preserved by arbitrary pullbacks. In other words, if we have fibered products, which I guess we don't know if we do yet. So if we have, let me say the general statement that if this is nice, if you have a very nice map, you have an arbitrary map, then this fiber product map should be nice too. But we don't even know, for example, that schemes and varieties have fiber products. So, but let me just point out an example that in some cases we do. So for example, if this were an isomorphism, then, and this were arbitrary, then in fact the fiber product exists, because that would be an isomorphism. That would just be W, and that would satisfy the universal property. So it does exist, and isomorphisms, it is true that isomorphisms are preserved by fiber product, and that's kind of dumb, maybe. So let's try open embeddings. And now, again, you might worry that, well, we don't know that fiber products exist. But in fact, we can just do it in this case, and this will be useful, that I will tell you what the fiber product of an arbitrary morphism is with an open embedding. And the answer is if there's X and there's W and it's horrible, and U is this nice open thing, then if we take the pre-image of this open thing, let me call this thing pi, and this is the pre-image of U, then because this is a continuous map, well, it's a map of locally ring spaces, then indeed this is an open embedding because I defined this in such a way. And then you can check that this satisfies the universal property. And that means that that is the fiber product, and better yet, kind of by, well, not quite by construction, that we proved that not only does the pullback exist, but the pullback is also an open embedding. So once again, both isomorphisms and open embeddings satisfy these three nice things. And basically, whenever someone tells you, "Oh yes, there's this morphism there, this is like a proper morphism, a projective morphism," you would want all of them to satisfy all these these conditions, and you will be upset. You should be upset, rightfully so, if they do not satisfy all three. Unfortunately, sometimes you'll be upset, but fortunately, not very often. Okay, so and so now we're set to. So let me just sum up to say that as examples, we're going to see are things of quasi-compact morphisms and the weird notion of quasi-separated morphisms. In the case of quasi-compact and quasi-separated, we define a quasi-compact scheme, which is something which has the finite subcover property. And I will just do the definition right now, which is that if you have a map from X to Y, it's quasi-compact if for every affine downstairs, the pre-image is quasi-compact. So that's how you turn properties of schemes into properties of morphisms. And so a scheme is quasi-compact if it's mapped to spec Z is quasi-compact. That could be a way of putting it. Why is this well defined? How do you know that, well, it is well defined. I gave you the definition, but it suffices to check on just a single affine cover. Why is that? It's got to be the affine communication lemma. So now you're welcome to just think about the affine communication lemma, realize that this notion trivially satisfies the hypotheses, and therefore you've just defined quasi-compact morphisms, and the same thing, we'll define quasi-separated morphisms, and next week we'll see lots of different types of morphisms, and the affine communication lemma will really come into its own and will make these far more painless than they might otherwise be. So that's what we'll talk about next week. Now it's just after 9 o'clock here Pacific time, so now would be a good time to end today and move to questions. So I should, maybe I should also say that I'm using a mic, not a great one yet. So I'm also curious whether this sounds better than the previous ones. No one's super complaining, so I guess it means it can't be terrible. So let me now go back. So let me end, and I'm going to move things around on my screen, which may mean I may lose my slides. And if I do, just let me know. Two questions. So yeah.
Okay, so I'm here now.
Great. And let me see. Great.
All right, so should I just fire ahead?
Yes, go for it.
Let me just look at these questions. Let's see this question thread. If there's anything. Well, okay. So so here's one that we can talk about. So what is a rational point? So people were talking about rational points a little bit, and I think a lot of people don't have different ideas of what a rational point should be, and
That is a
and
good.
maybe you talk about the.
That's a good question.
There's a problem with this word, I think. Yeah, I mean, you already
Yes.
mentioned it a little bit, but
Rational point is a problematic word, and so I should say you're great. That's a great question because both it's a natural one now, and we can answer it now too, which is from.
and I
A
can say
reasonable
I
point
can't
of
see
view.
anything that you're editing right now.
Thank you. That was what I was fearing was going to happen. Let me try this. Whoops, that did not work.
And then in this, I was going to ask you about what's a Q point of, say, a scheme defined over C. Maybe this is kind of something weird that happens sometimes,
Right.
like where it's not defined. You know, this issue of that if you have a relative scheme, right, and you ask
Right.
for like a Q point, then it just breaks. You know. Anyway, I just wanted to put. Yeah, so I'll let you go.
Great. Let me see if this
It was working a second ago.
Oh, it was? Okay. Well, let's see. I may have undone it. Great.
Looks good. I
Is
can
that-
see your wiggle.
Excellent.
And
Great.
then your cursors or your mouse is on the screen still. There you go.
Now it's gone.
Yep, gone.
Excellent. Okay, great. When someone says rational point, what do they mean? I think there are probably only two meanings, but there might be more that are out there, which is the first thing is a Q point, which means a map of spec Q to something, or if and that those are the rational number. That's very reasonable. But another thing it could be is if you are over a field of any sort, that like the real numbers, for example. And when I say over it, now we even know what we mean because now all I mean is we're working in the category of schemes over the real numbers. What is a rational point? Well, it means, let me replace R by K to make it less confusing. It means a map of spec K into it, where this is where I could call it a section. That may be a bit confusing, but it is a section. And so it's a K-valued point when once you said what your field is. I don't know why I guess I know why they call it a rational point, but I'm not thrilled by that. But that is what they use. And the issue Taylor mentioned is you could take something like, if you take C join XY, let me do it this way.
Great.
If you were to do if you were to apologies, sorry. If you were to try to solve x squared plus y squared minus 1, and you wanted to find, let me just do an example of maybe z, and you wanted to find rational solutions, this is indeed maps of spec Q to this thing. Or if you want to find complex solutions, you'd have no problem. And maybe and similarly, if you just thought about working over the rational numbers to begin with, everything still works fine. And the weird thing to watch out for, and there's nothing really complicated, you just, if you were to say that's the thing I'm looking at, x squared, if you were too sloppy and say x squared plus y squared equals 1, and you are talking to your complex geometer friends, and so you are talking about this, then you can't talk about rational solutions in this way because there's just no way to map rings in the opposite direction. And the problem is not the polynomial. The fault are the complex numbers. You cannot map the complex numbers to the rationals. So you have to be a little bit careful when talking about the functor points. If you are a number theorist talking to a complex geometer, you have to work over Q. You can't work over C. And then you have to work over the most restrictive or the simplest field.
Yeah.
Okay.
Great. So, so we haven't really talked about closed subschemes yet, but there was a question about if you had a map of rings and then you looked at the ideal, right? What does that ideal have to do with geometrically? So what I'm trying to get at is the scheme theoretic and set theoretic closure, what the difference between these two things are. And
so
maybe we can
great.
have a little bit of discussion about like what the set theoretic image is and what, sorry, the set theoretic,
Absolutely.
different
Well,
images.
let me, this will be a good way of setting up ideas for next week or the week after as well, that we already know that if you have an ideal of a ring R, we already know that as a topological space, that we have that spec of R mod I is a closed subset of spec R. So certainly you would expect this to be some sort, you should be able to make this some scheme morphism. And the answer is, well, of course, yes, because you have spec R, any ring map gives you a map of schemes. So you have something which is generalizing the notion of, it's the right notion of closed subset, but now we have the notion of closed subscheme. So why are we not talking about it? A good question is why we've talked about open subschemes. Why would we not talk about the complementary closed subschemes? And the answer is open and closed play very different points of view, and it's a red herring from point set topology that they are somehow complementary. And maybe as a metaphor, let me say that, and I think this is actually, I think there's a lot to this metaphor, but there may not be that much of the metaphor, which is when you have a group, you can have subgroups and quotient groups. And it's true that for every, well, okay, maybe it's not such a great metaphor. And they have very different roles. And so, for example, if you say one thing which will be relevant later on, when we talk about locally closed things, the notion of a subquotient. Well, is that a sub of a quotient or a quotient of a sub? And if you think about this a little bit, and I'll let you think about this a little bit, one of those two is the right answer and one of them is the wrong answer. So, okay, so we need to figure out what that means. We have pictures already. In some sense, in the case of affines, you already know what it means. You're going to have in the, right, I guess let's see, I'm not sure how much I should say, but if you take this and you map that to the plane, we have already seen that this is going to be the y-axis with a little bit of fuzz. So somehow the ideal is telling you, and we already know the ideal is telling you about that fuzz. We don't know how to globalize this. We don't know how to talk about this for a scheme in general, but affine wise, we do know what happens. And you could even basically define closed subscheme, not basically, this would be correct to say that affine by affine, it's of the form R mod I. And actually then you can use the affine communication lemma and prove this is well defined. And then you could say, what does it mean? And I'll say, look, you know what it means. And then you'll say, well, what's the geometry? And I'll say, look at the picture. And after a while, you'll stop bugging me and you'll just kind of become at peace with the fact that that is geometry. Okay, actually, I'm not sure if I answered the question or whether I went sideways with it. So I'll.
Did you do anything with the set theoretic closure?
Not yet. Well, so the notion of set theoretic closure of something is, so you might, so I guess, let's see if I can.
I was just talking about the map of, on the topological spaces, you can just take the image to the point. You know?
The image, so the problem is set theoretic closure and scheme theoretic closure don't play well together in pathological situations. So what is true is that in the case of spec R mod I to spec R, that map is what you are, we already know what it is topologically, and it's a closed subset. And the issue of closure of a topological space is actually problematic because let's see if I can, actually that one I'm going to table for 1 or 2 weeks because the weird things are going to happen.
Yeah. Yeah, it's hard to get so. I guess
I may
there's
misunderstand what you're
reduced,
trying to.
induced scheme structure, but if you want to do with non-reduced things, right? You can't just take the image of your points and then hope that there's a unique scheme structure. I mean, there's a reduced one, right? But if you want to do anything that has fuzz, right, then you're going to run into issues, and you have to deal with this scheme theoretic closure, which means that automatically things are going to be closed, And we haven't talked about closed yet, so I think maybe that's a time to.
And we don't even know how to put a reduced scheme structure on an arbitrary closed subset, although we almost do. You can check that on an affine. If you have some closed subset, then you just take the ideal of functions. We've already defined the ideal of functions vanish on this, and that is radical, meaning that spec of R mod I is reduced. So as long as that's like a nice, well-defined thing that plays well when you do this affine by affine. So yet again, you may want to use the affine communication lemma. You can check that if you have any closed subset, you can give it a reduced scheme structure. And if you think a little bit harder, and we will think harder, then in fact it's the only possible reduced structure. It's the smallest possible closed subscheme, whatever that means, that lives there.
All right. Okay. So someone asked if, so what was the question precisely? So someone was asking about whether rational points imply rationality.
Right. And the answer is definitely not, because you might know about elliptic curves. I'm not.
But they had, let's see, they had a way of saying this about curves. Let me see. Maybe the state was incorrect though. Oh, I can't find it right now. Anyway, yeah, keep going.
Okay, well, let me then say something which they may have been asking about, which is, okay, maybe we don't know what curves are yet, but if in doubt, let's play it safe and say, let's just talk about equations. Let's try to solve things in the plane that are that in two variables. That certainly better be, as long as f is not 0, that should cut out a curve. And it's true that all curves are birational to a plane curve. Actually, that's a worthwhile thing to say why that's true. Now that we know what birational is, and you could say, and let's say f is irreducible, which will mean that the curve is irreducible. In fact, integral. And you could say things like, does rational mean lots of points? Lots of points. You can definitely have finitely many. And the answer is almost. But this relates to something big and huge and wonderful. So it is true that we don't know what the genus is, but if you're to take the complex points, not the rational points, and you can, because now you know what complex, that's a great example. Now we want to talk about complex points, C-value points. And you can take them, and I guess you can close up. It turns out that you don't get a Riemann surface exactly. It may be missing some points. You may have some points where it's glued to itself in strange ways, but just take the Riemann surface that it's trying to be. Separate all the points where it's glued to itself, add on any points at infinity. And it turns out that if the genus is bigger than 1, then there are only finitely many rational points. And that is like an amazing, amazing, amazing fact, that the topology of this curve affects the rational solutions. And just to be super duper clear about that, these are the complex solutions, the real solutions are kind of just this real one-dimensional thing living on it. And then the question about the rational solutions are just things on here. So somehow all these holes that aren't part of the picture tell you about that, somehow forced to be only finitely many rational points. And now by rational points, what I mean Q points. So that's an example. So it's also true that if it's rational, then you have infinitely many Q points, because rational means it's rational, it's birational to A1, and that's got lots and lots of points. Every open set's got lots of points. And now the problem is there are some curves that are not rational that have infinitely many points. And these can't have genus bigger than 1. And we talked about the ones of genus 0, but they can be it turns out G is 0. If you have 1 point, you have infinitely many, and it's rational. But you have elliptic curves. And there are, as much of the audience knows, elliptic curves that have infinitely many rational points. And so they're borderline between spheres, which have one kind of curvature, and genus bigger than one things, which have negative curvature depending on your point of view, and spheres are positively curved. And these things are flat, and they offer this border. This is border region. So infinitely many rational points does not mean rational.
But there are, in a different direction, right? A quadric hypersurface, for example, is rational over K, assuming it's not degenerate, if and only if it has a K point.
That's true. Actually, that's a good one. That a rational, if you have a smooth, if it's not degenerate, if you have a smooth quadric in any dimension, if it has 1 point, 1 K point, well, oh, great. And actually, Julia, now you see why you want to mix the rational points with rational points. That
Yes.
She said, yes, exactly. So if it has 1 rational point, then it has infinitely many, and and a good start for that, which is going to be in the homework questions. If you have just in P2, if you have a conic that is smooth, whatever smooth means, and you know what it means, if it has 1 single point, that's rational, then it has infinitely many. And what's the argument? It's stereographic projection, and if you take the P1 of lines through this 1 single rational point, you take these lines, and I only want rational lines. So they look like, if you y equals mx plus b, for example, mostly, where these are rational numbers, and you intersect it with this conic and work out what the solutions are. Well, and so what you do when you plug this into the crazy equation for the conic, you get some quadratic in x, because it was degree 2 in x and y, and now you replace the y's. But this quadratic has 1 solution that's rational, and that means the other is as well. So in other words, this other point has a rational x coordinate, and similarly it has rational y coordinate. So every single line, rational line, will give you another rational point, and then of course any rational point will give you a rational line. So that means that mostly the points of the conic look mostly like points of P1. So that's basically roughly a reason why it's birational to P1. In fact, it is P1, isomorphic to P1. And Juliet's suggestion of the quadric surface, you could try the same thing, and you'll get that this is mostly P2. And here it really is mostly. It's not exactly P2. And it's interesting how it's not. And there's also a problem in the homework where you can try solving, for example, here's finding all the solutions to something like this, all the rational solutions to something like this. And so it's a Diophantine problem, but using geometry and using this geometry and starting from the fact that there is a point, I guess 0, 1, 1, 0 will work, W, X, Y, Z. Okay, good. So I'll let me.
I
Yep.
think the original question was something to the effect, if a variety has a point over every field, does that mean it's rational? So that might be an opportunity to talk about unirationality.
Yes.
That property sounds
That is good. Yeah, so great. So, okay, so if you have, right, so the question is, maybe if X has, let's do this over, I don't know, then we're going to talk about over the integers, or what do we over Q, has a point, well, that's bad. Then I'm actually not, okay, okay, so maybe I'm not sure, Jonathan, I think you have something in mind that I'm not exactly sure what it is, but let me give you an example of something with lots of points that's not rational. A different something that's not an elliptic curve, which is, what if you had something rational and you surject it onto something else that's not rational? Well, then this is like lots of points. Think about this as like Q to the N. And so this is lots of points too. So you can get things which look rational but are not rational. But then the worry is, how do you know it's not rational? And it's actually hard to give an example of something which is dominated by something rational, but is not itself rational. And in particular, if you do the case of curves, in fact, there's no such thing. If you have a map from a rational thing, which looks like a sphere, to something else, then it turns out topologically, so topologists will tell you that if you have any map like this that's orientable with positive degree, well, there is no such map like that. And so, in other words, any dominant map, roughly speaking, from something rational, like that's a CP1, it must be rational. And algebraically, since we talked about dominant rational maps correspond to field extensions, what it means is that if you have any subfield of C adjoin X, and this thing better be the fraction field, the function field of a curve, so its transcendence degree, it should be a finitely generated field extension of C, transcendence degree 1. Then if you have any subfield at all, in fact, it turns out that it must be the function field of something rational. It must be of the form C of Y, for Y is some function of X. Those are the only subfields of C adjoin X. Okay, this is a lot. This is definitely going sideways from the questions, but hopefully it's interesting. Oh, I should say this is called Roth's theorem.
Yeah.
And I guess where did it go? Here?
I think so.
Okay. Yeah, we do the American heavy metal band thing and like do like great. Great. I'll let that go away so no one sees it.
John, do you want to add anything to this about unirationality? Should we...
No, I mean, the property was not literally the same thing as unirationality. It just suggested the idea.
Okay, so all right. So one question people asked was, so you said that if you had a map of graded rings, right, then this induced a map on proges where on the source you remove parts of the irrelevant ideal, right?
Right.
One question we asked is this bijective? So is it true that all maps of proges are like this? And the other question, the other thing that I was going to ask is, what's so irrelevant about the irrelevant ideal?
So the irrelevancy of the irrelevant ideal.
One point.
Maybe I'll answer the first one because the second one requires me to like speculate and say vague things. So a really important.
And then maybe I'll prime you a little bit too while you're gathering your thoughts. Is that maybe you want to say something about saturation too during all this?
Yep. Or I want to mention the word saturation and carefully not say much about it. So if you have, let me do this the right way. Yes. So, okay. So when you have rings, you have a map from B to A, then you also have a map from schemes in the other direction. And this is this really is like exactly the same data. And so this is really what makes life really happy. And for graded rings, unfortunately, we have the following fact that if you have, I'll just put subscripts, B dot to A dot, then you have there's all sorts of problems with maps like this. So with things in the other direction, first of all, you may need to throw stuff out as we've discussed. You need to throw out where V of the positive graded piece of blah, 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 what I mentioned earlier. So first I have to throw out stuff, but let's even toss that in and say we're in our hypothesis. It's that we are assuming this fact, which will make this an honest morphism. Then for every map of graded rings, you have a map of proges, and you might say, great, do map of proges correspond to maps of graded rings in the opposite direction? And the answer is, well, first of all, the fast answer is no. There are maps from proges to proges that don't come from map of graded rings at all. And there are multiple different maps of graded rings that give you the same maps of proges as well. So it's horrible, and you could try to figure out how to make it better. And I almost want to say, I very much want to say, you really don't, that's when you think it's going to, that this is a good thing to do because these are elementary things. It's graded rings, it's projective geometry. Surely this is easier than scheme theory, and it is not. So, so if you take a graded ring proj of S, you might hope to make a better version of S, like the best version. So, and the best version will have the same proj. Will have the same proj. And you can, and this is a notion that relates to saturation, but it's not, there's even a map, I hope I get this right, from S to the best one. I may have the arrow wrong even at this point. And it's not worth it almost. So, and if you later on have, it's true that if you have modules, I'm offending some people, except the people most likely to be offended probably are not watching right now. But they'll,
Macaulay,
I'll
two
get
people
hate.
might be offended. I don't know.
Yes,
I mean-
exactly. Well, I mean, when I say it's not worth it, I mean, it's hard and it's important and useful if you want to actually calculate stuff, but it's hard. It's what I mean is there are things that are easy and things that are hard, and some hard things are important, but this is something where the payoff is not, you're not going to get easy. The things that are easy with projective geometry, you don't need this. And so you need this only when it gets hard. So I think just as with the topologist, I'm going to eat my words later. But for sure, I'll say at this point, I feel like when you're learning about varieties, what matters is only the one direction. And you should be curious about the other direction and want to know the answer. And pleased that there's an answer that's like, just like instead of sheafification, there's niceification of graded rings. And similarly for graded modules, you can do exactly the same thing. I should have said it, which is that you get a, well, no, you get a sheaf on proj of the thing, and you could ask, even if this S is a really nice ring, and you might say then, okay, then there's this recipe that turns modules into these kinds of sheaves, and then there's a best one, which is called the saturation of the module. And the right way to think about it, I think, is, well, no, this is not really true either, but you could think about it. For a certain kind of person, the best way to think about it is to not worry about it for a while, wait until you have cohomology and line bundles, and then you could define everything much more cleanly in that way. But you could also define it by hand. And maybe the best evidence might be of what's good and what's not good about it is if you look in, so I think Hartshorne, when he does things with graded rings, you might find it confusing. Whereas if you read it in Eisenbud or someone who's sort of more natively a commutative algebraist, things are much cleaner. Although they're cleaner because Eisenbud puts them in perspective, and the perspective is actually bigger. So it's worth learning about, but most worth learning about as part of something bigger. And when you try to do something kludgy to try to prove something in projective geometry, you suffer more. That's my opinionated answer.
Can I add that proj is really a presentation of a space or a scheme as a quotient of something by a group action, and what you can, if you have the same space can be presented as a quotient in many different ways. But maps that respect that presentation are exactly the ones that correspond to maps of graded rings. So,
although even there, that's not exactly true.
The sort of irrelevant ideal issue, but
exactly.
Yeah.
So here's now where the irrelevant ideal comes into it. Why is the irrelevant? So if you have a graded ring and you want to think about proj, well, a good thing to do is to take spec of this graded ring, but you want to, so what is p to the n minus 1 over the complex numbers? It's c to the n, throw out the origin, and mod out by c star, and you get cpn minus 1. So what Jonathan is saying is that you take spec of this and you throw out the closed subset. What closed subset? What are the things that are irrelevant from this point of view? It's the irrelevant ideal. And so you throw out where the irrelevant ideal is, you mod out, and now I can't say c star because I don't know what field I'm talking about. So the word for that is just GM, which is like but it's the same thing, the multiplicative group. And then this thing maps to proj, and this will be a quotient, whatever quotient means. If you think about quotient correctly, it's got to be the quotient. And so the things that mess with the irrelevant ideal, you get a new graded ring with some stuff that only involves irrelevant ideal, and that's not going to affect the story at all. And that saturation is all about, saturation deals with, okay, let me do one last picture, and then which is, here's my picture of spec of S dot, and there's my picture of where the relevant ideal is living. And you can imagine it's a scheme, it's got some fuzz, and it's going to be kind of cone-like because of this graded ring, but it could be some fuzz, extra fuzz here. And somehow what you want to do is chop off the fuzz and then take and that's the thing which you want to take the quotient of. So anything that has any extra fuzz here doesn't matter. And now I'll use words. There's associated prime or associated point, which is where which is a word for the excess fuzz. You can, so if there's no associated, if there's no extra fuzz, if this is not an associated point, then that's your best incarnation, for example. Let's see what else I should say that's related to that. Okay,
I think explicitly that the vanishing of the relevant ideal is the fixed locus of the.
Yes. Oh, that's good to say that in fact GM is acting on the spec, and this thing here is exactly the fixed locus.
Yeah. I also wanted to bring up, so we talked about the functor points today, and I don't think we've talked about what a group scheme is. And you've already brought up GM.
Yeah,
and
I mean,
so
before we go
maybe-
there though, I would say, I think something, for those who are more algebraic in nature, the words you might be wanting to look up now are local cohomology and things related to that.
Oh, yeah.
And really what Robbie's suggesting is that there's secretly two different rings and ring constructions here, one more algebraic and one more geometric. And their relationship is exactly via this algebraic tool called local cohomology. That comes up in many places, and it has beautiful interpretations in terms of geometry. And
so actually the kind of person I would ask about that would be someone like Juliet.
By the way, in the chat, derived functors came up. So during your analytification talk, there was a discussion about the direct image functor and injective resolutions and stuff. So
excellent.
We could even
let me
actually define local cohomology probably.
Great. So
I guess we haven't defined the colon. Do we need the colon?
Yeah.
Colon ideal. We've not yet defined it.
But we did say saturation. So
we did. So let me say that this is so. Let me make the order of ideas. If you do happen to know about local cohomology because you're coming from that background, then you will understand the geometry much better because you have this better, bigger picture. In fact, later on, if and when we do cohomology, that's going to be very simple if you already have seen local cohomology. And so Karen Smith, I should say, when I was maybe a postdoc, Karen Smith gave a graduate course on local cohomology using, I think, Mel Hoxter's notes. And it was like it was like a really fantastic, life-changing experience. So she'll actually give a talk on our seminar in a few weeks. So I sort of advertise in advance. She's like a spectacular speaker. So definitely, if you know local cohomology, then all the things that you're hearing about saturation and so forth, everything becomes much simpler. And so it becomes much simpler when you have the right, more general point of view. And if you're doing it in a kludgy way, then you're going to suffer. So I feel it's better not thinking about saturation until you're ready to think heavily about the commutative algebraic, or it's homological / commutative algebraic questions around it. It's not going to make the geometry simpler. It's going to make it clearer only once you have a deeper understanding. Would that be? I don't know if any of the shepherds disagree with that or have a different take on that. So local cohomology is really phenomenal. Yeah,
I think that it's useful from a computational perspective, all this local cohomology stuff, because if you want to put it into a computer, that's what you have to do.
Yes.
And
Uh,
again, I just want to advertise the book. There's a book called 24 Hours of Local Cohomology, which is this excellent introduction to a lot of these commutative algebra concepts. That is.
And local cohomology you can learn from I bet there are people who understand it theoretically very well who couldn't compute their way out of a paper bag, and vice versa. That somehow it's a very versatile tool. It is really worth learning because it's very well. It's extremely fundamental. Maybe I shouldn't say it's really worth learning because people might feel they are obliged to go and look at it. But if you get the chance to, you should be very happy to learn about local cohomology because it makes a lot of things clear. Yeah. And then derived functors, was that the, I wonder whether.
All I was saying is that we had talked about derived functors and what they were because of Gaga and this analytification, this map between the two ring spaces, right? And that, and DZB was saying that if the derived functor for push forward, if those vanish, then that's equivalent to the Gaga. And so,
right.
So there was some people started asking about what these derived functors were and how do you do this for things, and so I just said a little bit about what an injective resolution was, and then how to do this, and that it's just really the same in these categories. We've already talked about abelian categories, so
yes.
You know.
So with Gaga, maybe I should also say what Gaga is because lots of people will know and lots of people will not. Which is roughly speaking, if you have something which is compact. And I'm saying roughly because I don't want to say the word proper yet, but you have a variety over C. And by variety, I mean algebraic. Any algebraic variety over C that's compact in the appropriate sense. Let me say projective. And you could try to do algebraic constructions or complex analytic constructions. And Gaga says basically that you get the same answer always. And the reason is going to be, so you're going to need the compactness somehow. And if you squint, the Riemann existence theorem also fits under this because you have your analytic space and you have your original space, your algebraic space. Don't mean to pick sides in this battle. And you want to compare things upstairs and downstairs. So you might do that by pushing forward, and you want things to be an exact functor. And then this may, if you were brilliant, might lead you to develop the notion of the fact that of flatness, which is exactly designed to make cohomology, higher cohomology vanish. But you could say, actually, I should say you can duck derived functors here.
Can I say something here real quick? Is that people people were worried that you were going to try and do derived functors on schemes and worried that schemes were not an abelian category.
Yes,
and so
I definitely will not.
What categories there? Yeah.
Yes, so worry not. I will not do derived functors on schemes. In fact, with schemes are the advantage that derived functors, so whenever the statement is, whenever you're in a world where cohomology vanishes, you might hope to just do it directly without derived functors because it means something's exact. And that's what Sarah is. Actually,
all I'm saying is that you're working with the modules on the schemes or on these spaces, not the spaces themselves.
That's right.
All I wanted to point out. Yeah.
Fantastic. Great. So now I'm not sure whether I've answered the question or whether I've gone sideways.
I didn't mean to cut you off. I think
I don't know. I'm not sure what else I was going to say. Yes, but if you want to know why he invented flatness, that's exactly, no pun intended, why he invented flatness, to make this theorem work. But then anytime you have some thing which makes cohomology vanish, then that is like the ideal dream. You always sleep well that night after you discover such a thing. Okay. Now I forgot what.
If you remember what you were going to say, just jump in.
I don't. I don't at this point, but someone can ask again later if they.
So one thing that is related to this is someone was saying, okay, you have local coordinates in this analytic setting, right? And is there a way to do local coordinates in the algebraic setting as well?
Yes.
So I think
good question. Right. Local. There's the meaning of local coordinates, and so here is what you should expect. And actually, I think I should just directly say this, which is if you have m mod m squared, think about that as whenever I see this, I think about just the origin in affine space if it's smooth, and then the linear. This will be like the linear terms, and so local coordinates should be functions that span the tangent space, span the cotangent space. So if you take any set of things which span the cotangent space, so for example, let's just do with x, y, and z, you could take x, y, and z as local coordinates, but you could take x, y plus z to the 9th, y plus z plus x, y, z, and y plus x to the 19. And these would be local coordinates too. And so the notion of local coordinates should not be surprising at all. It should just be things that span the cotangent space, or it's the same thing as saying that they cut out in the local ring. They should cut out exactly, scheme theoretically, just the point. So for example, y and y minus x squared are not good local coordinates because they cut out something which is not scheme theoretically. So the scheme theoretic intersection, what am I saying? What I'm trying to say is that something very elementary, like what local coordinates are, already the notion of m mod m squared and the algebraic version differentials are already present in the story too.
All right. Yeah. So it's the system of parameters is the answer to that one. So another question.
Let me just write that down quickly. That says, right, local coordinates, some people will say system of parameters. Well, I should be a little bit careful because there's also the notion of like a regular sequence. How far can you, okay, there are local coordinates. Now, let me just not, let me not say more because I always forget. Yes, go on, Joe.
Yeah, so one thing so just completely changing gears is, so is there anything where spec doesn't commute with the ring construction, or can you just treat it completely the same?
What do you mean the ring construction?
Oh, like do all products turn into co-products and do all,
Oh, no, yes, but necessarily because it's the same category.
Yeah.
And we've even proved that.
Yeah.
The category is rings op is equivalent to affine schemes.
Or are there limits in affine schemes which are not limits in schemes, maybe?
Will they be co-limits though?
Yeah. Well,
but within the category, within these categories?
Schemes. Within the category of schemes,
schemes.
are there like limits or co-limits in the category of rings which do not correspond to limits or co-limits in the category of schemes?
It would be the other way around.
Is David here?
What's that?
Is DZB here still? Or did he leave?
It sounds like there's an example you want to show about one, like it depends on, in that case, have to go through which limits and co-limit. I need to think about each single one separately, but if you may have an example already in mind of something where there's a limit you'd want to take on one side, probably the ring side, I would think. And
there are examples, but I can't remember one off the top of my head, but I know that there's examples that you can get messed up where if you try to you assume that the construction in the rings will be the same in the construction in the category of schemes, that it won't work out. So we've already talked about fiber products, and that one works out, right?
Right.
But there are some that.
But the reason it works out is because you have fiber products, you have tensor products on you have tensor products of rings, and that by this equivalence, that means that you have fiber products of affine schemes, and then there's a good reason why that will go up to be fiber products of schemes. And so there's like I don't want to necessarily get into it, but it's the fact that sheaves, it really comes from the fact that a scheme is like the maps to a scheme form a sheaf, and that sheaf locally looks like an affine scheme. And so for that reason, fiber products which you define of sheaves are sheaves, and fiber products of affines are affines. It's a purely formal thing, but the arrows have to be going in your direction for it to work, basically.
All right. So I've got some more soft questions. So, okay. So here's one. Here's a good discussion question. Is that so? Is there a nice equivalence, a representative for equivalence classes of things that are birational?
Okay, that's a good.
I don't know.
So
That's
you'd
really,
so you'd really want right. The question is there right? So in the case of curves, you may already know, or the questioner may already know that in the case of curves, the Riemann surfaces are the smooth, compact, the smooth, projective, irreducible curves are the best, are undeniably like the unique one you would pick to be the best one. For surfaces, it begins to become mostly there is one, but there is a classification of surfaces, and depending on your point of view, some of the cases there won't be best possibles, but there'll be some where there's a tie. But in higher dimension, one of the maybe huge insights at the start of the 1980s when you try to make classification work for higher dimensional things is that the right thing aren't necessarily the ones that are smooth. They are things instead that are singular but not too singular. That counts as smooth enough. So the answer roughly is no, there's no single, there's not expected to be there's not a single best one in absolute generality or expected in absolute generality.
all right. So another kind of soft question is, why should we be thinking about morphisms instead of the objects?
Oh, okay. Where do I? This is the sort of thing where once you go through the looking glass, you can't sort of go back. You'll notice lots of times you will you will prove things like how. Let's see if I have that. Okay, so just this is sort of it's hard to give an example that is not going to, let me just try this, see whether this works. Like, let's say you have something and you want to show this is a nice object, and you have a map to another object and you know that that is already nice. If you have a notion of morphisms being nice, then as long as you have a nice morphism to Y, then you're going to have, then if you think about things as really being properties of morphisms, so nice now means to the class of a point or the final object, then because nice is preserved by composition, that means that X is nice. So it means that you can show that things are nice by thinking more generally about when morphisms are nice. So it's a strict generalization. Similarly, when we talked about quasi-compactness, that's a good example that we've already discussed. Let's see, how do I make this disappear? I don't know. Let's see if that works. Nope. Okay. It's going to be very handy to talk not just about quasi-compact. The reason quasi-compactness is a useful notion will turn out to be the same reason why it'll be useful to think of as a property of maps from one thing to another. This is tough to answer, except because it's going to be so absolutely, it'll get used so often, like all the notions you think about. Another example would be separated, or which is Hausdorff. When you make Hausdorff, that's something which you normally think of as something about objects when you first learn about it, and then later on you want to have it as a property of morphisms. Then you realize that I'm trying to think of like a best first example where it's like, oh yes, that's really useful. Let me tell you the wrong answer, which is, here's something which I feel like it feels so fundamental that I feel like people should know about it far earlier than they do, but it's not so, I'm not absolutely convinced. If you have so let me call this thing the cancellation theorem. And it's very formal and short to say, which is if you have a map from, if you have commuting maps like this, and you're in some category, and you have that this is nice, and you want to say that this is nice, so you want to somehow subtract off this morphism. So the hypothesis is that if the diagonal map is nice, then you can subtract like this. And this is very useful because, for example, things that are Hausdorff, that means that the diagonal map is nice in all sorts of ways. And then you can say any map to a Hausdorff thing, any map from something nice to anything Hausdorff is going to be nice. So there's, I guess I have no way of, I just cannot extract things from, yeah, okay. I'm just going to shut up because I think I'm not successfully, I'm not successfully.
I mean, it works. I mean,
yeah.
So one thing is that you can capture all the notions that you originally had, and then,
there's no cost, right? From one point of view, there's no cost. Exactly.
Yeah.
But if you already had a notion, let me put it this way. If you had a notion and you turn it into a property of morphisms, and there's like a fairly easy general way of doing it, which is if you have an abstract thing and you have a property of that variety or scheme, the way you turn the property of morphism, you say, I want the preimage of every affine to have that property. And if that's nice in the sense of these properties of morphisms that I described just at the end of today, if it's local on the target, if it's preserved by base change and things like this, then you've learned something new about your original. I mean, that means that your original class of objects is even better than you thought. It's so any right notion of objects better be nice in these ways. Okay, we're definitely getting philosophical and soft at this point.
Yeah. So people are like, Taylor, where are you getting all these questions from? So sometimes when you guys start discussing things, I write down questions for you guys. So,
right.
Here's a good question: is how do you know when a birational map or a rational map extends to a morphism?
That is in general a tricky question, except let's see, which example will I do? So Hausdorff is going to be, so let me give examples. One is that if you have a curve and you're mapping to something compact. So we don't know what curve is, we don't know what compact is. So proper or projective. But then limits exist. So if you were to take a curve like right, so let's say you have a map from A1 or the integers, say, to projective space, except it's not defined at one of the points. And so then you can extend it over that point. So there's a statement that any smooth curve, you can extend it as long as the target is compact. This is like limits exist. One parameter family is limits exist. And the reason is dumb and easy, that if you have a map from, say, the affine line to projective space, what does it look like? Well, it's basically going to look like a bunch of polynomials. And I guess they're n+1 polynomials. And the worry is that maybe they all vanish at 0, which will prevent it from extending. But then, or they might have poles at 0, which will prevent it from extending. But then you could essentially just multiply or divide by enough copies of X to make them not all vanish at 0 and have no poles at 0. And that tells you how to extend them. Or clear 2's out of the denominator if you want to do the same thing arithmetically. Another example is when you take reduced things and you map to something Hausdorff, that you can always, well, no, then that's not a good example. Okay, let me stop there and say that it's going to be something very special like that. And almost that's the only example of something which automatically works.
All right. So I think I'm going to close it here.
Great.
There's some other, but I think you covered most everything, and I think this is a good place to stop.
Great. So next week we'll meet at the same time, and I should say right now, in some ways, I feel like I try to see whether we're moving faster or slower than I expected. And in some ways, I realize we're moving faster and slower than I expected. And I'm somewhat mystified as to, I mustn't have been thinking very clearly. But I think it's faster than expected per time of me talking. But partially that's because there's a week in between and I'm leaving a lot to people watching to figure out because people know different things. Okay, see you all next week. Thanks for being here.